Hello everyone. Thank you for joining us for this latest edition of our AMS webinar series. Today's topic is mold machining with MecSoft CAMS plugins. Before we get started, want to make sure everyone can hear me. If for some reason you can't hear me or you can't see our screen, just let us know in the chat window and we'll see if we can make some technical corrections. Before we get started, just a few housekeeping tips. This webinar is being recorded and will be made available to you within a couple of days. Also, during the webinar, you can use your chat window shown here on the screen to ask us questions. Just type your questions in there and we'll be able to get to them throughout the program. If for some reason we can't, if we don't have time or we run out of time, we'll follow up with you via email, make sure that your questions get answered. We have a very special guest with us here today, one of our users, Al Grifka. Al is the CNC manager with Conley Manufacturing. Al will be talking about how he uses RhinoCam in his shop to produce tool and die components. We also have Uday with us. Uday is going to do a demonstration a little bit later in the program, and Joe's with us as well. He's going to be chiming in if we have some questions that need to be answered, and he may be popping in and out as we go as well. And my name is Don. We'll also be talking about some general programming techniques that you can use for machining mold cores and mold cavities, primarily mold cavities in this program, using both 2 and primarily 3-axis toolpath methods. We'll also discuss choosing the right toolpath method to achieve the best results in your mold machining. Also, why our 3-axis advanced toolpath methods are best suited for mold machining. And Uday will be pointing those out as he does the demonstration as to which 3-axis advanced methods are being used and why they're being used. Now, without further delay, I wanted to introduce our special guest, Al Grifka. Al is a CNC manager at Conley Manufacturing. Al has been using RhinoCam for the past 6 years for tool and die, as well as mold machining applications. How you doing, Al?
Pretty good, pretty good.
Take it over, Al.
All right. Yes, my name is Al Grifka. I am CNC manager at Conley Manufacturing, located in Shelby Township in Michigan. I have been using RhinoCam for about the last 6 years to do design molds, fixtures, and also mostly as a CAM software to lay cutter path and to actually cut the details and cut the molds. One of the things that I really like about RhinoCam is that the cost effectiveness compared to MasterCam, and also another thing I really like about it is the ease of use. It's really easy to use, and these webinars, explain a lot of the stuff or a lot of the questions. So it's nice to be able to go back and rewatch the webinars, stuff like that, to really get a good idea of completing the operations. There's a lot of tool paths that you can use. There's a lot of different ways that you can do things. It's a really useful tool here at our shop at Conley Manufacturing.
Al, what do you do there at Conley Manufacturing as far as your customers and your processes? Can you tell us a little bit about Conley?
Yeah, so at Conley we do a lot of automotive and aerospace work. For automotive, we primarily do checking fixtures, which for those of you that aren't familiar with checking fixtures, an automotive process, when the parts are coming down the line, they'll use a jig, a checking fixture to check the parts, say for the buttons that are on your radio or even your door panel, your mirrors, glass, your hood, any kind of engine component, any kind of steering components. So basically what we do is we'll replicate a fixture that will hold that particular part in a certain manner to be able to check it so that when the parts are coming down the line, they may pull, say, one out of every 5 or 10 or 20 parts and put it in this fixture and check it to make sure that their process in the production process is working correctly, and it's a safe fail where they can catch bad parts coming down the line, and maybe they might have to alter some of their processes to make that part perfect every time it comes off the line. And then we do also mold work for aerospace. We'll do like layups for carbon fiber, stuff like that, fiberglass layups, molds. We'll do injection molds just for all different types of airplane, aerospace type of parts. So primarily we're aerospace and automotive, and then we also do some customer-related things. We'll see later in the model that we're going to look at here. So in the next slide here, so here's a couple pieces that I've made. These are actually, this here is a mold. It sits inside this other piece. You can see there's a through hole here. This would be one of the datums. This is what lines up down here in the bottom of the hole, and then there's a vac groove here, and then they'll use an injecting process to actually inject. This, I believe, is for a rubber injection. So they'll inject in there to make the part, form the part, all the walls, all this contour on top and on the bottom. So this part here would actually flip right over, fit right inside there. The vacuum grooves and everything would sit right inside there, and it would locate off of this datum here and this datum here. Same thing with this part on the bottom. This here will go right through that hole upside down, as you see, and there's half 13 key inserts in these holes here. A lot of times in aerospace, a lot of the material is aluminum, obviously to make it lighter, but they'll have steel key inserts on the insides here. So this part fits right inside here. As you can see in this picture, that's it. Actually, the parts mated together. On the end here, there'll be I believe it's a quarter pipe tap, and that's what they'll use to hook up their injecting processes, their injection hoses, and stuff like that. So then on the next slide, these are a couple other things that we do. This piece here was actually a prototype for aerospace company. They wanted us to make 6 of these. It's a vacuum coupler, I call it. What they'll do is they wanted 6 of them. This is would be the end of the vacuum where it would suck from. They wanted to check suction pressure. So once they got it to their facility, they were going to use different size hole patterns and different size hole schemes to see what kind of pressure that they could get from that. So on the bottom of this the inside of this is all hollow. This is where it would hook up to their vacuum port. It's basically the head of the vacuum. This here would be like a strapping fixture. So there's 2 dowels for location, and there is 2 tapped holes to hold it down. That would most likely be flipped upside down to hold some type of beam or hold something to the side of the plane or the inside. There's some countersinks and some grooves down in here where there'd be a feature that would stick through on the other side for like a hoist ring or something of that nature. This down here is actually a checking fixture, part of a checking fixture block. So they'll, as a production process, they'll stamp. This is to check sheet metal steel parts, typically between a 1/16 and an 1/8 inch thick. So they would set the part on top of this. It actually wraps around the other side here, and then here they would use a feeler gauge to check part tolerance. Same thing like right here on this top part. These here would be the nets or the datums where the part would actually sit at. And then same concept here, they would use a feeler gauge to check the contour of the part here. There's a couple of bushing holes where they would use go, no-go pins or gauges to make sure, again, that once the parts are coming down the line in the production process, that everything is perfect or within spec for them to be able to continue their production processes. So then on the next slide here, this would be one of more of our customer specialty things. This actually was for a friend of mine. He has a few injection molds at his house and in his garage. It's kind of like a home workshop. So he wanted me to design a two-piece mold for him using a part positive, which is this here. So I designed this in Rhino, took the part positive, did a split where I wanted my parting line at here, did a couple different operations to make sure my parting line was right on the edge of the glass of the frame itself where I wanted it at. And then we put some holes here for locating the two parts together. And as you can see, got quite a few small cutters that will be going down in here. And this is what RhinoCam was really good for is, say maybe one cutting operation doesn't quite meet your needs. There's multiple different cutting operations and parameters that you can set to really get down into the fine detail and making sure, especially in a mold, that your parting lines are really good, because in a mold, anything that is not quite correct is going to show up on your final part. So with RhinoCam, it was really easy to put my part positive in there, make a box around it, check where my parting line was going to be at, and then half the two molds, basically. And this part here we're getting ready to cut. We haven't cut it yet. We cut one out of Delrin, then we ended up changing a few things to it, cut it out of plastic, and eventually here, the next week or two, we hope to cut it out of aluminum, like 6061, and check how it mates up to itself and everything like that. Put it in the injection mold and inject a few parts and see how it looks and see if we need to alter anything. And then from there, we'll see how many parts that the jig will last for being made out of aluminum, and then if need be, we'll make it out of steel.
Okay, Al. Sorry to interrupt you, Al. Go ahead.
No, that's just getting ready to hand it back over to you, Don. And yeah, if anybody wants to check out our website, it's kindlymanufacturing.com. And yeah, nice talking with everybody.
Okay, Al, if you could hang with us a bit, we may have some questions come in from our attendees. They may have some questions for you, so if you don't mind hanging around just a bit, that would be great.
Absolutely.
Okay, if we could go to the next slide. Great, thank you. In this slide, in the next couple of slides, we wanted to talk about some techniques you can use for machining at the parting line, because as Al mentioned, the most critical area of any cavity is the parting line. And if you don't get the parting line right, you're going to have problems with the injection molded part. You're either going to have flash, or you're going to have irregular parting lines. So what you're seeing here, you got two sides, one on the left and one on the right. We got the same part, the same tool path. We're using advanced 3-axis 3D offset pocketing to do the cavity. So the only difference in these two applications is that the one on the right has what we're calling a guide surface. Now, for lack of a better word, you can call it whatever you want. It's just an extra surface that's in your part model that's displayed when you generate the tool path. So without the surface displayed, if you look on the left, you see that the tool will ride up the side wall of the cavity and then ride on the parting line, because you're using the parting line as your control boundary to cut the cavity. And when the tool rides that parting line, you can clearly see, if you look at the image below, which is the cut material simulation, you can see the degradation in the parting line. You can see where the tool rolls over the parting line, both here and here. And on the right, with that guide surface displayed, you see that the tool remains vertical and doesn't roll over the parting line. So the side of the tool cuts the parting line as the tool goes up and starts rolling up onto the guide surface. And if you look at the cut material simulation below, you can clearly see the quality difference between the parting line. And again, the only two differences here, same parameters, same surface, same toolpath, is this surface is displayed when the toolpath is generated. So let's go to that next image. Oh, I clicked too many. Let me go back one. Okay, what I wanted to show here was just some examples of some guide surfaces for the mold that Al showed us. And basically what you're looking to do is you're looking to mask off the cavity. And not only to mask off the cavity, but also to extend past the insert boundaries so that you can get a clean cut past your insert. So here on the top left, you see a general masking surface that covers the entire cavity area as well as extends past the insert boundaries. In the top middle, you see a surface that completely covers the cavity alone. And then if we look over to the top right, we see a surface that covers the parting split plane, and it extends out past the insert boundaries. Now, if we look at the bottom row, on the bottom left, you'll notice that this cavity has two islands in the middle for these center pieces where the lens go in the glasses. And there's a guide surface on that island top that it is the same surface as what's in the model, except that it extends a little bit past the parting line. And we'll show you why in just a moment. And then in the bottom middle, you'll see this is the one where I showed you in the previous slide where we showed a guide surface extending up vertically from the cavity. This is what it looks like along the entire cavity parting line. And that the extension of that really only needs to be 1/2 to 1 times your tool diameter that you're going to use to cut that cavity. So we extended it a little bit higher here just to illustrate the point, but it only needs to be about the radius of the tool. And then on the bottom right, we just show a cut material simulation here. So let's go to the next image and I'll get into a little bit more detail here. Okay, on this big image on the left, you can see the cavity insert and you can see the guide surface that we added on top of this island. And in the top right image, this is what we mean by cutting at the parting line. So in the XY, when we're cutting this area, and this is all 3D contoured surface, there's no flat area on this parting line. So with this guide surface displayed, and we select the surface here on the part as your control geometry, and we set the end condition to past, which means the tool is going to go past the parting line, and with that surface displayed, it has a place for that tool to ride as it goes past. So you're getting a nice clean movement from the parting surface, past the parting line, onto the guide surface. And that's what you want for when you cut the parting lines in the X and the Y. In here, over on the top right, you'll see what the tool paths look like without the guide surfaces displayed. You have the nice extension past the surface boundary, which is the parting line. And these tool paths, although you'll be cutting some air, but that's to be expected to get a clean cut past your parting line. And that's another point I wanted to mention here. As you look at these extra surfaces that we're using in this technique, and the little bit of air that we're cutting, as you know, you probably have cut some molds or some inserts yourself. You want to take the extra time and the extra accuracy to get this parting line correct. I mean, this is going to be your master part in order to produce your production run. So taking the extra time to do it right up front is going to keep you from having to come back and rework this mold if you got issues in the molded parts, especially at the parting lines. And then down below in this image here, you can clearly see the nice parting line that is created using the technique that we're illustrating here. So here is just another view of the cavity, and this is the same image you saw on the previous screen where the tool paths extend past the parting line. But here in this image in the middle, these are the guide surface that are displayed when the tool path is generated. So let me explain again what's happening here. We're selecting the surfaces to machine. We're using the boundary condition of the surface to control the end of the cut. And we're telling it that we want the end of the cut to go past the boundary surface. So when it does, it starts riding on these guide surfaces, and it keeps it from rolling over the parting line and then rolling down into your cavity. So that's what you're trying to avoid. And down here, it's just some other images of the cavity toolpath itself, where the tool rides up the cavity, and when it gets to the parting line, it just keeps going up to the top of the guide surface here. And you can clearly, again, see the difference in the cut material simulation. The top here on the right, no guide surfaces were displayed. You see where the tool rode over the parting line here and around here. And particularly right here where you got this fillet, and the tool, if the tool rides the edge of this parting line and gets to that fillet, you're going to have a dimple right there for the radius of the tool where it cut into the fillet, and you don't want that. So in the bottom image, you can see the clear, nice, precise cut parting line with the use of these guide surfaces. That's it for the slide portion. We're going to hand it over to Uday now, and he's going to show us more detail about the particular part that we was talking about and the techniques that we're talking about. Uday?
Thank you, Don. Thank you, Al. Hello, everyone. We will now take a look at how we actually program this part in RhinoCam for the cavity that you just looked at in the slides in here. And today we'll be focusing on our RhinoCam product. So the workflow would be very similar if you're either using RhinoCam or Visual CAD-CAM or our plugin for SolidWorks or even a LibreCam. So the process of creating the toolpaths would be very similar, except that the host CAD systems are going to be slightly different between one another here. So without any further delay, we'll jump directly into a quick demonstration of how we could program this part. So what I currently have here is the mold cavities that Al made available to us for today's webinar. And here you can see that there's two halves, and we'll focus on how we can program the first half in here. So your workflow would be very typical. You would define your stock geometry where you basically establish the extents of your stock material that you want to use for basically milling this part out, and then you go through the process of establishing your work 0, which could be the location where you want to put in your XYZ origin, or you could call this your fixture offset or your work coordinate offset. It could be like a G54 or 55. That's what you typically use for your work offsets. Now, in order to prepare this part for machining, typically in some applications you would want to make sure that the block of material that you're starting with is nice and flat at the top, so you would want to go ahead and add a facing operation to ensure that the top face of the block is planar, and you would also want it to go ahead and make sure that the sides, all the four sides are squared, which means at 90 degrees, so you would want to run a profiling operation. Now these methods are available under 2-axis, or also known as 2.5-axis operations, where you would want to maintain your Z at a constant depth as the cutter traverses in X and Y. So there's a wide range of two-axis methods that are available to you right from our standard configuration. You could program facing, pocketing, profiling. So in this particular part, we have programmed two operations. We have a facing operation where we are going to be basically just making sure that the top face of the block is nice and flat, planar. So we have inserted a facing operation, and then we also wanted to have a profile operation to ensure that all four sides are square. So that way when you place the workpiece, there isn't any offset, anything being created in here. So now these two operations, you could have this programmed as a separate operation, together, post them out to your machine, and then continue with some roughing and re-roughing operations in here. Now, the first step we want to do here is after the facing and the profiling, we want to rough this down to as close as possible to the finish shape of the part. And since in this particular mold, the cavity has a much smaller these features, we would want to basically mask some of these areas in here for the initial roughing and pre-finishing operations. So in order to do that, what we have done here is we've created some additional surfaces, and they're placed on different layers in here. So I'm going to display those layers. I'm going to display layers 1 and 4, and you'll see that a surface has been added to cover up all the cavity features on this particular model in here. So when we do a roughing operation or a pre-finishing operation with these large cutters, the tool would not cut into those cavity areas, so you would get a nice flow of your tool path in both roughing and finishing operations, and you can eliminate the tool from cutting into these cavities. So when you have these surfaces added and displayed, since the tool cannot cut into those cavity areas, you're basically kind of masking them by adding these surfaces in here. And that's exactly what Don had pointed out in one of the slides earlier as you watched it. So we have a 3-axis horizontal roughing operation program. So this is known as horizontal roughing, or also known as roughing in levels. As you can see, we're doing a roughing in levels or layers called Z-level roughing, or also known as horizontal roughing. Now you can find the horizontal roughing under the 3-axis methods. It is available right from our Express configuration. You have 3-axis horizontal roughing. So that's the first operation we would program in here to rough the initial stock material down to bring it as close as possible to the finish shape of the stock part. So we want to rough it in levels, layers, so remove as much material as possible, typically using like an end mill, a flat end mill, or you could be even using like a corner radius tool for roughing process. So in this particular example here, we are using a flat end mill, and as you can see, it's how nicely it's roughing it down in levels. You can see it in the simulation right in here. So by adding those surfaces, the tool is not cutting inside those cavity areas, which we will be programming in a later steps down the road. So once the roughing process is completed, you would want to go back and rough it again. You could either be using a smaller tool, or you could be using a same tool with a smaller or tighter step over, and you can also reduce the amount of stock you're leaving from the previous process. And for this, we are using a method called horizontal re-roughing, and this feature is available in the Pro and Premium configurations of our CAM products. The re-roughing operation takes into account the in-process stock that is being left from the previous step, meaning it takes into account what was already pre-cut from the previous roughing or pre-finishing operations, and it creates another secondary roughing operation to go back and remove some of the uncut material from the previous step. So in this particular step, you're not going to be cutting air, you're actually saving significant amount of time in basically going back and roughing it again, either with a tighter step over, a tighter step down, a smaller tool, or leaving less amount of stock from the previous process. So you're trying to rough it out again to bring it as close as possible to the finish shape of the part, so it makes it a lot more easier for your pre-finishing and finishing process. Again, on this particular operation as well, you'll notice that we have used an additional surface to basically cover those cavity areas, so we can go back and look at programming the cavities in the additional steps that we are programming down here. So we've generated two operations, a roughing and then a re-roughing operation. Now the next step is to basically go ahead and even out these stair steps in here that we created in the roughing and re-roughing operations. So we would start with a pre-finishing operation. Now for this you could be starting out with a operation like a parallel finishing. You could be using other methods as well. So in this particular example, we're using a 3-axis parallel finishing. And again, this method of parallel finishing is available in all the configurations of our product here. So in the parallel finishing, we have it specified to leave about 20,000 stock. So this will help in evening out the stock that's being left, the stair steps that were being left from the previous roughing operation in here. So I'm going to go ahead and quickly run a simulation of this so you could actually see the operation of the simulation in here. So I'm going to hit play. You can see the simulation of the simulated model of after the pre-finishing operation, so where we basically removed the unevenness, the stair steps that was being left from the previous step of the re-roughing operation. So you could repeat the pre-finishing operation, the parallel finishing operation again in here to go back and reduce the amount of stock that's being left. And take a look at this tool path in here. So since we had the surface to mask in here, the surfaces in here, you'll see that the tool is not going into the cavity areas, so it gives a nice transition in here and gives you a nice flow of the tool path without having the cutter dip into the cavity. And also it's critical that we want to maintain a sharp edge on these parting lines in here. So that's one of the reasons why we've added this surface to basically hide or mask those cavity areas. And you can see the tool path in here also has a very nice transition in these areas as you go from these steep sections down to the sculpted areas here. Look at the nice transitions in the tool path, and also you can see the arcs being fitted to the tool paths. So you can have arcs being fitted in all the 3 principal planes, which is your XY, XZ, and YZ planes. And in this case, you can see arcs being fit in the G18 plane, resulting in a very nice cut motion in here. And there's the simulation of the second pre-finishing operation, where we are taking it down from a 20,000 stock down to a 10,000 of stock in here. And this can be set under the cut parameters, which is the stock to leave. So it's basically leaving a uniform stock of 10,000s above the part surface in here. So this would be a pre-finishing operation. Now in this particular case, you will notice that we are using a curve region where the tip of the tool will stay up to this region in here as part regions for control geometry to contain the tool path. So these are the 2 pre-finishing operations we programmed. Now in the next step, we're going to go ahead and look at how we're going to rough and re-rough the cavity areas in the mold. So in order to demonstrate that, I'm going to go ahead and hide a few layers in here and display layer number 7. So as we pointed out earlier in the presentation slides, in order to establish a nice sharp edge on these parting lines, what we have created is an extension of these surfaces. So the wall surface has been extended up in the z-axis, as you can see, and these extensions can be equal to a tool radius or the tool diameter of the largest cutter you plan to use for programming these cavity regions in here. So these surfaces can be extended by at least your cutter radius or cutter diameter, so that the tool path that as you generate will basically go past it, and this will result in a nice sharp edge and not having to roll over to the adjacent surfaces. So this is how we can create some extensions. And if you're using Rhino, you have a lot of different tools for creating these surfaces. And so in other CAD systems, whether you're using SolidWorks, or you should be able to model these surface extrusions using the surface tools that are available to you in here. So we now have the cavity roughed out. Again, we're using a re-roughing operation. Now the point I'm trying to emphasize here is with the re-roughing operation, it takes into account the in-process stock that's being left from the previous step. So it knows the amount of material that's being left. So it knows that these areas have already been roughed out and pre-finished. So when you program the re-roughing operation, you're only cutting and removing material in the cavity areas, and you're not cutting air, you're not cutting any additional material. So this is one of the very nice way to save your programming time and machining time and make your workflow a lot more efficient. So the re-roughing operation can be found in the Pro and Premium configurations of RhinoCam, and you'll find it right in the advanced 3-axis methods, horizontal re-roughing. So in this particular process in here, we are selecting drive regions, which are could be face edges, or it could be selecting a curve. And again, we are leaving about 30,000 stock to initially rough out the cavity areas in here. So that would be the first step. And then we want to rough it down again using the same re-roughing technique to basically take it down in smaller increments. We're going from 30,000s down to 20,000s, and then we are basically roughing out these top surfaces in here. Now let's talk about how we created these surface extensions for the top surface in here by creating a surface that extends past the lens area in here. You can see that we have a surface now that extends past these areas so that you get a nice parting edge along the mold cavity in here. So in order to establish a nice sharp edge around the cavity, we've created a surface extension in here to extend past this. Now, one of the things I would like to point out in this particular operation is we are not using a part region for control geometry. Instead, we are selecting what is called a part surface. So you can select surfaces for machining. Now, this surface selection is available in all of our configurations. And as you select these surfaces, the silhouette region is automatically generated by RhinoCam, so you don't have to create any additional regions in here. And once you have these surfaces selected, you could also set the surface extend condition. So setting the extend condition to past will make the tool go past the surface by your cutter radius. Selecting as 2 will maintain the cutter completely inside, like a pocket operation where the cutter will completely stay inside the silhouette boundary that it's created. Now selecting the on condition will keep the tip of the tool on the geometry. So you have all of these nice controls with part surface selection. So we can choose to go past, or you want to keep it to, or just on the silhouette of the silhouette that's generated from the surface that you selected. So in this particular case, we would want to go past, so which would result in a nice parting edge for the cavity in here. And as you can see, we've selected to go past it. And as I'm going to preview the toolpath, you'll see that the cutter goes past, on the based on the surface extend condition that we've set. And again, here we are programming a re-roughing operation on these lens areas in here. So you can see that the toolpath you're generating is basically you're progressively removing material down in steps going from one level to the next. So these are the re-roughing operations we programmed for the cavity regions of the mold. Now in the next step, we're going to apply some pre-finishing operations in here to finish the mold cavity to bring it down to the part surface. So again, I'm going to go back and enable these surfaces 1 and 4 on layers 1 and 4 to basically go back and finish it down to the part surface. And in this particular case, we are using a surface selection. As you can see here, we are using part surfaces. You can select 1 or more surfaces, and the system will automatically generate this silhouette for all the surfaces based on the surfaces that you selected. And you could specify your surface extend condition in here as well. So you could use a combination of drive regions where you can select curve, edge regions, surface edges, or you could select part surfaces. As you can see here, you don't have to create any additional curve regions and directly select those surfaces from your model. And RhinoCam or our CAM plugins for other products will also automatically generate those silhouette boundaries. So in this particular step, we are basically finishing it down to the actual surface of the part. And again, with the surface extend condition, this would achieve a nice sharp parting edge in these areas in here. So that's what's most critical when you're machining mold cavities or more cores. You want to make sure that the parting edge is nice and sharp. So in this particular step, we are creating a finishing operation for these areas on the mold. As you can see, the simulation here shows a very nice finish, and you can see the nice sharp edges that are being created because of the surface extensions that we've added in here. Now, in the next step, we are creating a finishing operation again to again clean up some of the additional areas with a much tighter step over in here. In this particular case, we are again using a parallel finishing operation by selecting part surfaces, and you can see that the angle of cut or the direction of cut is set to 90 degrees. So in the previous operation, we cut angle of cut was set to 0, which means the tool path travels back and forth parallel to your x-axis. By changing the angle of cut to 90 degrees, you can remove any scallops that may have been left from the previous process in here to result in a much nicer finish. So you have very precise control on the direction of cut, the angle of cut that you can set in this parallel finishing operation in here. Now, in the next step, we are going in and finishing some of the additional features on the mold cavity in here. And in this particular step, we are actually programming the top of the lens feature, and we are using a surface to extend past in here. So since we had done a pre-finishing or a pre-roughing operation, we want to go back and finish these areas, so that would result in a nice sharp edge around these cavity regions in here, as you can see. So I'm going to go ahead and hide the display of the layer so you can see how nicely the toolpath extends past the parting edge. So this will help you create a nice sharp edge and not having the cutter to roll over into the cavity. So by creating this extended surface, you will ensure that the cutter will go past it, and which would result in a nice sharp parting edge on your mold. So we also added another finishing operation in here by changing the direction of cut. So in this particular step, we are cutting across. We're changing the angle of cut to 90 degrees. So whatever scallop that you may have noticed are being left from the previous step, which was set to parallel to X, which was 0, is now basically cleaning it back again by changing your angle of cut into parallel finishing. So you're basically repeating the same operation and changing your angle of cut to result in a very fine finish on these cavities in here. Now the next step we are doing is a pre-finishing operation for these cavity regions in here. So there's different techniques that you can apply. In this particular step, we are first doing a pre-finishing of the cavity and leaving some stock, about 10,000 stock. So we're doing a pre-finishing operation with a parallel finishing operation using a ball mill cutter. And again, we're using the surface extensions in here to go back and clean these up with a pre-finishing operation. Now once the pre-finishing operation has been completed, we would then go back and run a finishing operation in here, and you could use different techniques. And one of the techniques I would like to point out here is the use of a 3D offset pocketing toolpath. And this particular method, which is offered in our Pro and Premium configurations, you will notice that the generated toolpath creates a uniform 3D step over. This technique is also known as constant scallop machining, or also known as 3D offset pocketing. This would result in a very nice finish and produce great toolpaths when you're working with mold cavities or mold core features in here. So you can take advantage of some of these advanced 3-axis toolpath methods that are offered in our Pro and Premium configurations, and look at the a nice transition of the toolpath, and it maintains a uniform 3D step over, and it works great when you have both cavity regions or when you have steep areas. So you could use the 3D offset pocketing to achieve really good finish on these cavity regions on a model. So here we're programming a 3D offset pocketing, and this is done with a 30-second ball mill to get to all the finer details in the cavity region. And you can see the finish on the toolpath and the quality of the finish that you achieved with the simulation. And again, by using those surface extensions, you'll see that you're resulting in a nice sharp edge on the cavity, on the sidewalls of the cavity in this mold. Now finally, you would want to go back and do some additional cleanups in certain areas in here. So in this particular case, we wanted to go back and do a precise cleanup towards the top areas on the frame here, and we have programmed this using a 3-axis 3D offset profiling operation in here. And you also have a very nice control on your exit motion, so the cutter is not retracting along the edge of the part. You're basically using a radial entry and an exit motion in here to basically result in a very nice transition as you're leaving the material, and the same thing as you're entering the material as well. So you have these control where you can basically apply different feed rates for each of these motions, starting with your plunge, approach, engage, and then your cut motions. Now with these surface extensions that are being displayed in here, you will ensure that the parting edge remains sharp and the tool path nicely flows into those extended surfaces. There was nothing additional you had to do in terms of generating the tool path once you had those surface extended on the model itself. And you can have these placed on different layers. So when you generate a tool path, you're generating the tool path for what's visible in here. So when you turn off the layers and regenerate the tool path, it'll only be looking at what geometries are visible to be able to program your tool paths. So we have 2 cleanup operations, one for the left and one for the right half of this here. As you can see it on the 3-axis 3D offset profiling operation. And again, this is one of the advanced 3-axis methods which is available to you in Pro and Premium configurations. And these methods give you the precise control that you need, which makes it a great set of toolpath methods for programming mold cavities and for tool and die applications. These are some of the very nice toolpath methods. Now, one of the other methods I would want to point out here is called a pencil tracing operation. Now, this technique, this method is used for doing your cleanup, and in this particular case, it automatically will identify those bitangencies to help you get a better finish, clean up these areas in here where you have bitangencies on the mold cavities, mold core areas, so result in a very nice finish and eliminating the need to go back and do some manual finishing on these processes in here. So the pencil tracing is a great way to clean up some of these areas in here, and which would result in a very nice finish. And this could be applied even in mold cavity areas. So the system will automatically identify those bitangencies and generate these beautiful tool paths in here for cleanup operations. Again, the pencil tracing operation can be found under the advanced 3-axis methods, and it's available in both Pro and Premium configurations of our mill module. Now finally, we've also added a curve machining toolpath in here to just go back and just clean up around where there's a nice transition between the floor and the mold section in here. So you could use a curve projection machining where the toolpath follows the curve, but it's actually projected down to the underlying surface geometry. So in the case of an engraving, the toolpath would just follow the curve but not checking against the surface model. But in the case of a curve machining, the toolpath is again checked against the the solid surface geometry, the mesh geometry that you're working with, and it flows nicely along the surface. Now finally, on this particular model, we've created those drilling and the hole making operations so that it can match the other half of the mold. So you have the drilling operations and the reaming operations programmed, and the hole making operations can be found under the hole machining methods under holes, and you can find it under drilling. You have drilling, deep drill, countersunk, break ship. All of these hole making operations can be found under these drilling operations. So what we looked at here is how we could program one half of this cavity here. So I'm going to go ahead and load the concave part of it and just quickly run through some of the operations that we programmed over there so that you get an idea of how easily you can program operations for both concave and convex half or 2 halves of your mold cavity. Now one of the strengths of our CAM product is being able to take the toolpath that you already generated in one of your parts or family of parts, and you can reuse them or apply them on other parts, where you can actually save these operations, what you programmed, into a knowledge base. So you can save the workflow of operations like the roughing, re-roughing, pre-finishing operations. You can save them to a knowledge base and take those operations into your other model, and you can apply them where you can load the knowledge base in, and you can basically edit the operations and select the geometries that you'd like to use for programming. So in this particular case, we have the same facing and the profiling operation that we programmed on the convex half of the mold. We're programming the same here on the concave, except we've just had to select a different set of machining region for it. So by reusing the knowledge bases, you're making your workflow a lot simpler, a lot easier, and you don't have to go through the process of rekeying the parameters in here for generating your toolpaths. So similar to what we did on the convex half, in the concave half we have a roughing operation. We have the re-roughing operation being programmed in here into these cavity areas, and we're programming a pre-finishing and additional finishing operations. So the workflow, what we did here is very similar to what we did on the convex half of the mold. So we're programming the concave half. So by this process, you can generate the toolpaths for both half of your mold very efficiently using our CAM product. Now with this, I would like to hand it back to Don.
So there are a few questions here. This is Joe. There are a few questions. Maybe there's a couple directed to Al, so maybe I can jump in here. So Al, one of the questions was, how long did it take you to design the mold? So if you can talk about that a little bit, that'd be great.
Yeah, to design it, it was about an hour or two. Basically, getting the part positive in there and then selecting where your parting line is going to be at, and then use a boolean command to separate them. So all in all, they had to edit a couple things. So it was probably an hour or two to get it where I wanted it at and everything like that.
That's pretty good. So there you must be an expert Rhino designer to get that in an hour, I would say.
Yeah, it was. I've done quite a bit of it. So.
Okay. Right. And there was a comment for you, Al. It says from one of our listeners here, this is a genius use of the tools available. So.
Oh, yeah.
That's a compliment for you.
Yeah, absolutely. Like that's one of the best things I like about RhinoCam is there's the possibilities are almost endless with the design, and then also with creating toolpaths. As Uday showed, there's a lot of different operations you can use to achieve the same results or even better results than what you may have thought was all that you would be able to do.
Okay, great. A few more questions before we wrap this up. There was a question, maybe Uday, you can answer this. What's the difference between 3D offset and projection pocketing machining? If you can talk a little bit about that.
Sure, I'll certainly do that. So in the case of a projection pocketing toolpath, the toolpath is basically being just, creates a uniform 2D offset, and the toolpath is projected down to the underlying, 3D geometry. So in cases where you have steep walls or, steep sections, you can see that the toolpath is probably riding along some of those side walls. So the 3D projection pocketing would be ideal when we have parts that do not have a lot of steep sections, like a shallow cavity. And in the case of 3D offset, 3D projection pocketing, the cutter will completely stay inside the boundary as well. So whereas if you look at a 3D offset or pocketing or 3D, constant 3D step pocketing, it maintains a uniform 3D step over in X, Y, and Z. So which would result in a much finer finish and better finish on the toolpath when you have both steep sections and steep and basically shallow sections on a model. It creates a uniform 3D step over, so which basically would result in a much nicer flow of the toolpath and the finish across the model. And in the case of a 3D offset pocketing, your tool tip will stay right up to the region that you selected in there. So those are the main differences between 3D offset pocketing versus the projection pocketing. Here you can see the transition of the toolpath is very nice, and it maintains a uniform 3D step over for both steep sections and for sculpted areas or areas that are not very steep.
Okay, and one more question for Al. Al, can you talk a little bit about how you did the alignment for the male and the female portions of the mold?
The alignment.
How do you keep the alignment straight? Do you use any kind of alignment pins, or how do you actually position these parts?
Yeah. So basically, there's two different. So for the alignment, I used reamed holes, and what I did is when I modeled it before I split the two halves, I made a hole going through both of them, so I knew that they were going to be in the exact same spot. And then again, I used reamed holes for those. So what I'll do is we'll take a dowel pin, put the two pieces together, and then press fit the dowel pin between both of them. Just want to keep in mind that you want one at one side of the mold and one at the other side of the mold, and the longest in the X direction, or a lot of times we'll do one corner of the mold and the other corner of the mold, and then use the two opposite corners you could use for screws, so that you could put the two dowels in and then use screws to hold it together, like
From the back side.
that.
Yeah.
Yeah. And then you can also use those same reamed holes for when you put it in your tool, that's your jig that's going to be going into the injection mold itself.
Okay, great. So Don, we have a time for a couple more questions.
Yeah, I think we got time. I wanted to go ahead.
Go ahead.
I just wanted to say here before we wrap it up, you will find a lot of information about these techniques in our blog, and also we just published a case study of this part with Al. So Al's a case study has also been published on our website just this week. And just also we have some blog articles. One in particular that's going to help you in cutting molds is if you go to our blog and look up for machining accuracy. It'll just give you a lot of the different places you can go to check your accuracy, make sure that you're outputting the decimal point places of accuracy that you need for your particular application, both in the CAD system and in the toolpath itself, and then also in the post-processor, and then also in your controller, just to make sure that everything's getting the amount of accuracy that you require. That's all I wanted to add. Okay, we've about come to the end of the webinar, everybody. We hope you walk away with some useful tips and techniques for your next mold machining project. As we mentioned, this webinar is being recorded, and it will be made available to you via email soon after we're done here. Have a nice day, everyone. Thanks for joining us.